The rest of these examples, we're going to use GeoGebra for this because we're looking for probabilities. So when we're in our GeoGebra, I want to make sure I have my probability pulled up. So I'm going to click on View. I don't need the graphics. I don't need the algebra right now, but I do want the probability calculator. So I'm going to leave that open. Now, because we're using the normal distribution, make sure that your drop-down menu says normal here. Looking at example 6, it says the Mystic River pH levels follow a normal distribution with a mean of 8.34 and a standard deviation of 0.4. pH levels below 5 or above 9 are considered unsafe for aquatic life. Each month, random samples of 60 pH measurements are collected for analysis. Part A says, for a single pH measurement, can we use the normal distribution to calculate the probability of an unsafe pH level? So the question here is asking for the population, not the sampling distribution. We're talking about single measurements. Is the population distribution normal? Because if it is, then we can use the normal distribution for the individual measurements. And it does. It says here that it follows a normal distribution. So we can use the normal distribution to calculate this probability. Now, the notation is going to look like this. If the pH level is unsafe, that's when the pH level is less than 5 or the pH level is greater than 9. So these are the probabilities that we need to find. So I'm going to make sure I'm on the normal distribution. I'm going to put in my mean is, let's see, 8.34. My standard deviation is 0.4. And I'm going to calculate the probability that x is less than 5 first. Since I'm doing a less than statement, I'm looking at the left wing. So I'm going to choose my left bracket. And then it will give me that option to say the probability that x is less than, and I'm going to put in 5. And I'm going to hit enter. And it's going to give me that the probability is super small. When we round it, we get 0. So I'm going to say that this is equal to 0 plus my probability that I get when p is greater than 9. Oops, I forgot my x. There we go. So now let's find the probability that x is greater than 9. So now I'm doing greater than. So I need to switch to my right bracket. And I want to put in greater than 9. So you can verify the picture here. My arrow's at 9 and it's everything greater than. That's all shaded in. And my probability is 0.0495. When I add that up, my final answer is 0.0495 for the probability of the water being at an unsafe level for pH. Okay, now let's look at part B. This is talking about the sampling distribution. So now we're thinking differently. We're thinking about the averages, and our standard deviation changes with that. For the sampling distribution of 60 pH measurements, we can use a normal distribution to calculate the probability that the sample mean indicates an unsafe pH level. Yes, the underlying distribution is normal. All the other qualifications are met. It's randomly picked. The samples are independent. It's the same sample sizes over and over again. That's 60. And the underlying distribution is normal. So we're not concerned about sample size, but even if we were, the sample size is big enough. It's bigger than 30. So we can use the central limit theorem here and use the normal distribution. So for the sampling distribution, we could use X bar for the average, but another way that you might see it is capital M for mean. So we might see that the mean, you can use M or X bar, the mean is less than 5, or the probability that the mean is greater than 9. Now, remember, the mean of the sampling distribution and the mean of the population is going to stay the same. What changes is the standard deviation. So instead of having 0.4 here, when we're dealing with the sampling distribution, we want to do the standard deviation of the population and divide it by the square root of the sample size. You can tell GeoGebra by clicking on this keyboard here and pulling up your keypad for the square root, or you can put in SQRT for square root, and I'm going to put in, what's our sample size, 60. Now, I did not put in the decimal value because when I put in the decimal value and round it, it's going to throw my answer off. So it's really a good idea to make sure you actually put in that statement with the square root. Now, I'm going to put in less than 5. And I want to make sure that I'm on the bracket that's facing left because I'm doing a less than. Notice here, everything is shaded above 5, which is not what we want. We want less than. So I'm going to make sure I change that bracket. Now, 5 is way off to the side, so we're going to get 0 again. Very, very small. Now I'm going to do the same thing for greater than 9. So I'm going to change my brackets. I'm going to put in greater than, and I'm going to change this to 9. And again, this is so small. See how 9's way off here? So the area under the curve is super, super small, just like the area on the left past 5 is super small because it's way out there. When we round it, we get 0. So this is also going to be 0. So our final answer for part B is going to be 0. Part C, using the sampling distribution of the means, determine the range where the middle 50% of sample means will fall. So because we're still talking about the sampling distribution, we want to maintain this standard deviation. Now, because I want to find the middle 50%, I know in each wing there's going to be 25%. So I have 25% in the left wing, 50 in the middle, and 25% in the right wing. And that way we can find our 50% in the middle. So I'm going to work backwards. I'm going to do my left wing first. I want my probability, the area under the curve for my left wing, to be 0.25. So that tells me my left bound cutoff for the middle 50%. So I'm going to put that in there. Left bound is equal to 8.3052. Now let's do the same thing, but on the right. I'm going to choose the right wing by choosing that bracket that's facing to the right. I'm going to put in that I want 0.25 for the right wing. Hit enter. I get that the right bound should be 8.3748. That's a very small window, but let's check it to make sure. If we want to do a between to check it, I'm going to choose these brackets. I'm going to do between 8.3052. That's my left bound. My right bound is 8.3748. Now, when we look at that area between those two values, left and right bound, look what we got. It's a little bit off because we rounded, but that's 0.5. That's the middle 50%. Let's look at example 7, analyzing visitor counts. The daily visitor count at the USS Constitution Old Ironsides follows a bimodal distribution with a mean of 1,200 visitors and a standard deviation of 150 visitors. A sample of 20 days is analyzed. So for part A, it says, for the mean of 20 days, can we use the normal distribution to calculate the probability that the mean of a sample is between 1,100 and 1,300? If so, find the probability. In this case, the fourth requirement is not satisfied in our definition. We can see that the population distribution is bimodal. So if it's another distribution, we have to make sure that the other requirements are met. But in addition, that fourth requirement must be satisfied so that the sample size is 30 or bigger. In this case, the sample size is 20. That is not big enough for us to be able to use the central limit theorem and the normal distribution. So I'm going to put in here, we cannot use the normal distribution and the central limit theorem because item number 4, that requirement number 4 in our definition is not met because of a sample size less than 30. Looking at part B, it says, for a single day's count, can we use the normal distribution to calculate the probability that a single count, just X, not X bar, is between 1,100 and 1,300? Because the single counts is a bimodal distribution, it is not normal. We cannot use a normal distribution for the population probability as well. So again, we would say no, the population is not normal, so we cannot use the normal distribution to find probability for single values. There we go. Let's look at our last example, example 8. At Ecocentric's Hair Salon on Newberry Street in Boston, the time for a complete hair coloring service follows a left-skewed distribution with a mean of 95 minutes and a standard deviation of 12 minutes. The salon wants to analyze samples of 32 appointments. Part A says, find the mean and standard deviation of the sampling distribution. So the mean of the sampling distribution is going to be the same as the mean of the population distribution, which in this case is 95. And this is minutes. Our standard deviation for the sampling distribution is what we get when we take the standard deviation of the population and divide it by the square root of the sample size. In this case is 32. So let's figure out what that is. When we round that to 2 places, we get 2.12. That's 2.12 minutes. Part B says, for a single randomly picked appointment, can we use the normal distribution to calculate the probability that X, a single value, falls between 90 and 100 minutes? If so, find the probability. In this case, we're going to say no because the population follows a left-skewed distribution. So when we're talking about the individual values, those are left-skewed. So I'm going to put it in here. No, the population distribution is left skewed, not normal. For part C, it says, for the mean of 32 randomly picked appointments, now we're talking about the means of 32 randomly picked appointments, can we use the normal distribution to calculate that the sample mean falls between 90 and 100? If so, find the probability. Here we can use the central limit theorem and the normal distribution. The samples are randomly picked. They're independent of each other. They're the same size samples over and over again. 32 is the sample size. And the sample size is big enough. It's over 30. We're talking about 32 for our sample size here. So we can use the central limit theorem in the normal distribution. So I'm going to put here, yes, the conditions are met for the central limit theorem. Let's find the probability that the mean is between 90 and 100. So we're told that the mean is 95. So I'm going to put that in here in my probability calculator. My mean is 95. Because we're dealing with the sampling distribution, my standard deviation is going to be 12 divided by the square root of our sample size. Okay, now let's find the probability that it falls between 90 and 100. Now we're talking about averages, so I'm going to do an in-between. So I'm going to choose this option here with the in-between brackets. I'm going to put 90 and 100. And we can see up here that the shaded area is between 90 and 100, so we know that we've got the setup correct. And this is going to be a probability of 0.9816. For part D, using the sampling distribution, find the time that bounds the quickest 20% of the mean times. The quickest 20% is the time that has the least amount of minutes because it's quickest. So we want to find the quickest 20%. So this is where we're working backwards. So since we're talking about the quickest, which means the smallest amount of minutes, we're going to look at the left bound because that's going to be where the smallest number of minutes are. I'm going to click on my left bracket. Now I want to tell GeoGebra to find that cutoff point that gives me the lowest 20%. So I'm going to put in here in my probability area 0.2. I'm going to hit enter, and then it shows me that cutoff point. So everything to the left of 93.2147, that is my lowest 20% of times, which is my quickest times. So I'm going to put here the time that bounds the quickest 20% of mean times is 93.2147 minutes. There we go. So the key takeaway to this lesson, when you're reading anything about sampling means, make sure you read the problem carefully, identify if you're talking about the single values that are randomly picked or if you're looking at picking means from samples. Because when you're finding the probability, you're going to approach that two different ways. And you also have to make sure when you are dealing with the sampling means that you make sure that if you're going to use the normal distribution to approximate the probability, that all of those conditions for the central limit theorem are met.